Perspective Class 3 Video 1. In this video we're going to talk about two-dimensional vectors and scalar multiplication of vectors. So let's begin with the definition of what a vector is. The general idea is that instead of interpreting a coordinate pair AB as a point in the Euclidean plane, we instead interpret it as a vector. And a vector is simply a straight line arrow with the end, the tail at the origin, and the head at the point AB. So if I draw a point here, AB, this is A, this is B, remember? Well, this is the point AB, and the vector AB is this arrow right here. So the arrow is the vector AB. And I understand that there's obviously a source of ambiguity here because I use the same notation to denote both the point and the vector. So I use this here to denote either the point or the vector. But in practice it's not that much of a problem, so I'm going to continue doing it. One thing I will say about notation is when you're talking about vectors, you tend to use a standard set of variable notations. So what happens when I'm talking about vectors, we tend to use either boldface, so for example like this, or you use this sort of notation. Okay. So if I'm talking about a variable vector, a generic vector, I'll probably use this notation here. So like V with an arrow on top is equal to AB. It's just the convention that you do. Okay. Also, when we talk about vectors in the context of like the vector universe, we call normal numbers scalars. So we call normal numbers scalars. Okay, and we tend to denote scalars by like lambda or mu or s or whatever. I mean, you can use whatever. There's no like law which tells you which letter you have to use, but it's common to use these letters. Okay, just like it's common to use this notation when talking about vectors. Okay, so when we're talking about vectors, we call the normal numbers scalars. So why do we care about scalars? Well, we care because there's this notion of scalar multiplication. So if you have a vector, V equals AB, and you have some scalar, lambda, and remember, lambda is just a number, so lambda could be equal to 2, for example. Okay, just some number. Then we define this thing here, lambda dot V, which is the same as lambda dot AB, and it's equal to this. All you do is you multiply each thing individually. It's as simple as that. It's really not that hard of an operation. Scalar multiplication is just you multiply each of the coordinates individually. This is scalar multiplication of a vector by a scalar. And we can do some examples. So 3 dot 1 comma 1. Well, this is 3 times 1 comma 3 times 1, which is 3 comma 3. You don't need to write this step out when you're doing this, but since this is our first time, I'm going to go slowly. This here is minus 2 times 2, comma, minus 2 times minus 1, which is minus 4 comma 2. And finally, this is 0 times 7, comma, 0 times 5, which is just 0, 0. Okay, so this is all examples of scalar multiplication. One thing to note, which you might have noticed from the last part of this example, is that scalar multiplication by the scalar 0 always kills the vector. Okay, and what I mean by that is 0 times any vector is equal to the 0 vector. Okay, 0 times any vector is equal to the 0 vector. Now I want to mention a geometric interpretation of what scalar multiplication is. This is all very algebraic, this stuff here, but I like to think about vectors as geometric objects. I mean, by definition, a vector is an arrow, right? So what happens to this arrow when I scalar multiply? That's the question I want to answer now. Well, we answer that with this theorem. Okay, so here's a theorem, and the theorem says consider scalar multiplication by lambda. So lambda is a variable in this case, okay? And it tells you that if lambda is bigger than 0, then the vector does not change direction. But if lambda is less than 0, then the vector reverses direction. And more specifically, I can break down into more possible cases. So if lambda is bigger than 1, then the vector gets stretched. If lambda equals 1, then nothing happens. I mean, scalar multiplication by 1 does nothing at all. If lambda is between 0 and 1, you shrink the vector, so the arrow just gets smaller. If lambda is equal to 0, you kill the vector. We mentioned this. Now let's do negative cases. So if lambda is between -1 and 0, you shrink the vector and you flip the direction. Because right here we said if lambda is negative, you flip the direction. If lambda is equal to -1, you just precisely flip the arrow's direction, and you don't stretch or shrink it at all. And finally, if lambda is less than -1, you stretch the vector and then you flip the direction. Or you flip the direction and then you stretch it. It doesn't matter which order you do it in. Okay. So what does this look like geometrically? Let's do an example. I'll draw some sort of coordinate axes, like this. So 1, 2, 3, 4, 5, 6, 7, whatever. 1, 2, 3, 4, -1, -2, -1, -2. And maybe I'll let the vector be 2, 1. So if I plot this, it looks like this. This is the vector v equals 2, 1. Okay, and now I'm just going to consider what it looks like when I scalar multiply v by different scalars. For example, 2 times v is equal to 4, 2. So that's 4, 2. It's up there. So 2 times v is that vector there. How about 3 times v? That's 3, that's 6, 3. So that's all the way there. So the vector starts at the origin and it stretches all the way to the end. 3, like that. How about something different? So how about -1 times v? Well, that's going to be -2, -1. And if I plot that, that's just a direct opposite direction. -2, -1. So this here is minus v, or -1 times v. Same thing. Okay. So as you can see, when you scalar multiply the vector, you sort of stretch it in this way, or you flip it and you go the other way. But it always sort of lies on the same line. That's the end of this example, and that's the end of this video.